This is a talk about some big data problems inspired by signal processing, a little bit of structural civil engineering, although the talk will be mostly on the mathematical side, so consider these kind of stylized problems motivated by those applications. This is joint work with my current PhD student, Shuang Li. Some of this was work with my former PhD student, Jae Young Park, and with Anna Gilbert, the co-advisor of Jae. Parts of this are also in collaboration with my student, Dewei Yang, and with Professor Gongguo Tong. And Gongguo visited here a couple of months ago. For those of you who happen to see his talk, this will have a minimal amount of overlap with that. For those familiar with atomic norm minimization, he kind of focused on the single signal case. I can focus on the multi-signal kind of sensor network case. So we're interested in problems related to structural health monitoring. This is motivated by the problem of monitoring physical structures like buildings or bridges, capturing data over time and using that data to evaluate the health of the structure to determine if it's been damaged or fatigued, if it needs to be flagged for inspection or shut down. For these purposes, there's growing interest in using wireless sensor networks deployed across the structure to capture this data, transmit it to a central node, and then have that central node do the assessment of the health of the structure. The goal, or I come from kind of a compressive sensing background where we look at problems from the perspective of, can we solve this problem with a minimal amount of data? How little data do we really need in order to solve this problem reliably? If we can answer that, then that can help us to compress data, to minimize the amount of data that we physically have to sample, transmit, communicate over these wireless channels. That allows us to extend the battery life in these sensors and have some quantitative guarantees about the performance and so on. So a little more formally, the sort of problems we're going to look at, we'll have a structure, say with n sensors deployed across that structure. These are measuring signals, displacement signals, let's say vibration signals. Imagine this is a bridge, and we have n sensors deployed across this structure, monitoring how the bridge vibrates over time. So we have signal 1, signal 2, signal n. Each of these is a time series, a signal that oscillates as a function of time. We could stack those at any given time. We stack those into a vector of n displacements. We call that vector x of t. And then, of course, as time evolves, that vector of displacements is going to evolve. So we'll focus a lot on this time-varying vector of displacements. For structures that can be described by the sort of simple linear second-order equations of motion, then we have this equation describing the motion of x of t. Second-order differential equation, second derivative first, and then these coefficients are actually matrices, the mass, stiffness, and damping matrices of the structure. These capture intrinsic properties of the structure, and then g of t is an external forcing input to the structure. In general, m, c, and k would be unknown for the structure. G of t might be unknown as well, or you might have some control over it. But typically, we're going to focus on what you can infer from the collected data, this x of t.
So, just a quick question.
Yes.
So, the second order derivative of the first derivative is
element-wise, yes. Thank you. That's right. So we are going to make a further simplifying assumption that the structure is in free vibration, meaning there's no input currently being applied to the structure, but that it might be responding to some previous set of initial conditions. So the bridge was displaced, and then it's been let go, and a car drove over it, but now the car is gone, and we're watching the vibration. There's also interesting research in modal analysis about when G, the external input, is random, or when you have some control over G. Those are certainly interesting problems, but not what we're currently focusing on. Under our assumption that the general solution to these equations of motion says that x of t is going to be a superposition of these modes. So at any given time t, x of t will be a linear combination of k vectors, call them phi k. Capital K is the number of such vectors, the number of active modes. And these are length n vectors. They're called the mode shape vectors of the system. So at any given time, your displacement vector is a linear combination of these, and the coefficients here in that linear combination vary with time. In general, they're going to be exponentially decaying sinusoids. So the fact, you have a physical structure, it's been displaced and now it's responding. Eventually it's going to stop moving if it's a real structure. That's captured by the exponential decay of these sinusoids. To make it a little more tangible, here's some data from a bridge in Ypsilanti, Michigan, collected by the group of Jerome Lynch. These are the time series recordings from accelerometers placed on the bridge. Running a modal analysis algorithm reveals that there's 3 dominant mode shapes, shown here in blue. And at any given time, what that means is that the actual displacement of the bridge is some linear combination of these 3 shapes, some weight times this, plus some weight times that, plus some weight times that. And those weights, they change over time because the bridge is moving. And they change generally sinusoidally. The first weight changes with about this frequency, about twice per second. The third one is just a little quicker, and then the second one's a little quicker. The third one changes about 10 times per second, oscillates about 10 times per second. So the name of the problem that we're going to focus on is called modal analysis. That refers to the task when you're given samples of these displacements over time. So say in m points in time, we're going to record all these displacements from all the sensors and then say that those are delivered to the central node. We're going to try to estimate the modal frequencies and estimate the mode shapes of the structure. This is useful in structural health monitoring because let's say you know what the mode shapes look like when the structure is healthy. You go back later, you find the mode shapes again, and if they've changed, that might be a sign that there's been some damage to the structure. You might even be able to find it based on where the mode shape has changed. With that said, we're going to focus on guarantees concerning the actual recovery of the mode shapes and frequencies, and not talk further here about the sort of diagnostic process that follows. So there is plenty of related work out there in modal analysis. This is really a classical problem in structural dynamics for which there have been many algorithms proposed, some of which involve sparsity because there's relatively few active modes, some of which involve kind of statistical approaches, either source separation approaches or independent component analysis. This talk is not necessarily meant to propose a new technique that replaces all of these. What it is meant to do is to provide some theoretical analysis in an area where that is generally lacking. There's sort of very good practical understanding of which algorithms to use, but I think it's fair to say not a lot of theoretical support for a lot of the algorithms that are used in practice. So I'll get to which algorithms we're going to study in just a few minutes. To be a little even more specific about the assumptions we're making, we're going to consider a structure that has no damping in it. So this structure, if it was displaced and let go, would continue vibrating. It would not have that exponential decay. Practically, that's not reasonable, but it might be reasonable over short enough time scales. With that said, we're interested in extending the analysis I'm going to talk about to the damping case later on. We're also going to assume that our signals are captured in complex analytic form. So generally, the displacement of a physical structure is going to be a real number, not a complex number. But it's common, for example, in communication systems to convert from real valued signals to their complex analytic equivalents. To do that, you filter out all the negative frequencies in the signal. You keep only the positive ones. That converts these real sines and cosines, the actual displacement sines and cosines, it converts them into complex exponentials, j being the square root of -1 here, since I'm an electrical engineer. So in that case, x of t is going to have this form. It's going to be a linear combination of these k mode shapes, phi1 up to phi k, with coefficients that change sinusoidally in time, with frequencies f1, f2 up to fk. Those mode shapes and frequencies are intrinsic properties of the structure. However, there's also these coefficients, A1, A2, up to AK, and those are determined by the initial conditions of the structure. So if you set it vibrating, you displace your structure, you let it go, it's going to respond in a certain way. If you displace it in a different way and let it go, you'll get a different response. The only thing that's going to change in that response will be these coefficients out front, the A1 through AK. So those are determined by the initial conditions. And in general, all of this is unknown. I mean, the specific A's, F's, and Phi's are unknown. But from sample data, we would like to learn all of those things. So there are, just to quickly mention some other related work, there's parallels to this problem in the field of compressive sensing. Several people, including our group, have worked in what's called distributed compressive sensing, where you have a sensor network, you have a collection of signals that are all sparse. Say these signals, for example, are sparse in the frequency domain. You're interested in recovering those from a minimal amount of samples. The reason that existing compressive sensing theory can't be directly applied here is because the frequencies we're considering, these F's, are not assumed to be on a regular grid. In compressive sensing, the standard off-the-shelf theory only works when the frequencies are all multiples of some fixed harmonic. I'll also mention that while I've motivated this from the perspective of structural health monitoring, this sort of joint sparse frequency estimation problem arises in a lot of places in signal processing, including direction of arrival estimation and antennas and array processing. The analogy, the conversion there is that K, which is for us the number of active modes, is like the number of sources impinging on this array. And N, which for us is the number of sensors, corresponds to the number of snapshots in that context. And finally, since we're talking about estimating frequencies, it's just worth also acknowledging, like, this is a very classical problem in signal processing for which there's plenty of classical techniques, like the Prony's method and the music method for doing frequency estimation. Those all have various advantages and disadvantages, and this is not meant to sort of wholesale replace all of those existing techniques. But one notable difference is that none of those techniques are obviously compatible with the sort of random sampling and compression that we're going to use to reduce the dimensionality of our data set. I talk about sampling these signals in time, but we're soon going to talk about how to compress this data set while preserving its essential information. And it's not clear how techniques like this could be applied in those compressed settings. Okay, so what we're going to cover today are really two main topics, two different algorithms for doing the modal analysis. A common theme, aside from the problem that they're both trying to solve, is that they both involve matrix decompositions or factorizations. So speaking of matrices, there's one that's going to play a central role here. That's this data matrix X. Remember, we have n sensors, and we think about sampling these displacements at m points in time, t1 up to tm. So you could stack all of this into an n by m matrix, and we're going to call that X. And so these two algorithms we're going to consider reveal the modal parameters of the structure by doing some type of factorizing or decomposition of this matrix X. And then furthermore, we're going to think about how can we compress the problem to save on the data acquisition and to save on communication. So there's going to be some way of sort of compressing or minimizing the size of X as well. Any questions before I move on to some more specifics?
So here you don't assume those sensors are on a regular grid.
Spatially?
Yeah.
No, we do not assume anything about the spatial positions of the sensors.
How about the time?
So we're going to consider really a series of different protocols for doing the time sampling. We're going to start with uniform, and then we're going to look at choosing them randomly. Okay. So the first method we're going to consider is what's called the proper orthogonal decomposition. This is really an existing algorithm that caught our attention because of its sort of simplicity to state, but also because it's very widely used, at least as a sort of quick and dirty technique for doing modal analysis in the field. So remember, here's our data matrix. X, n is the number of sensors, and m is the number of time samples. The POD, sort of in our language, probably more familiar to people in this room, is to simply take the singular value decomposition of this matrix X. They have a name for the left singular vectors of that matrix when you do that. Those are called the proper orthogonal modes. And then you're done. The proper orthogonal modes themselves can offer an approximation to the true mode shapes of the structure. So here's a little more explanation of that. We have our data matrix X, number of sensors times number of time samples. You take its SVD, you get a matrix with orthogonal columns times a diagonal matrix times a matrix with orthogonal rows. And the left singular vectors of this matrix, right here, these columns, right? Notice that they're all length n, which is the number of sensors we have. Those columns are approximations to the true mode shapes. This has been known for a long time. There's even some theory for this, that under certain conditions, asymptotically, you get convergence of these left singular vectors to the true mode shapes of the structure, but that's as m, the number of samples, goes to infinity. So m, number of samples. So this matrix is getting wider and wider. We're interested in that fact, but we don't want this matrix to be arbitrarily large. We want to know how small can we make m and still have good approximation guarantees. So what I'm going to present are some non-asymptotic sampling bounds that we developed in the last couple of years. Again, we studied the POD because it's widely used and simple to compute and also supports some of the types of randomized compression we're interested in. It's only a way of estimating the mode shapes, not the modal frequencies. That's still somewhat practically useful, but we'll talk later about another technique that gets us the modal frequencies. It's also requires a particular assumption that these mode shapes, these vectors, phi 1, phi 2 up to phi k, are actually mutually orthogonal. To have the approximation guarantees, you need these to be orthogonal, in particular because the way you're estimating them is with columns of an SVD, which are themselves orthogonal. So to have convergence to the true mode shapes, those true ones must also be orthogonal. That can happen in practice, in particular if the mass of your structure, like your bridge, is uniformly distributed across your n sensors. In general, it won't happen. You won't have orthogonal mode shapes. There is a renormalization of the data that you can always do that will make your mode shapes orthogonal. But whether you know enough about the structure to do that renormalization may or may not be true. With that said, let's talk a little bit about the non-asymptotic theory here. So we're going to be sampling these displacement signals in time, and first we'll consider doing the sampling uniformly. So we need notation for the amount of time in between our samples. We'll call that sampling interval TS. We'll suppose that's chosen initially at the Nyquist rate, so inversely proportional to the highest frequency in the structure. And then we'll consider these m uniform sampling times spaced TS seconds apart. There's going to be a quantity of interest that plays a big role in our analysis, in our results. That is the question of how closely spaced is the closest pair of these unknown modal frequencies. The minimum difference between Fk and Fl, we scale that by our sampling interval Ts. That's going to give us a number delta F, which is between 0 and 1. Close to 1 or big values mean that the frequencies are relatively far apart from each other. But a value delta F close to 0 is going to mean that there's at least one pair of frequencies that are, relatively speaking, very close together. And we'll see the effect of that in every single bound that we talk about. Okay, so in uniform time sampling, again, we have a data matrix, n sensors, and m uniform time samples. And our result says this, and I'll summarize this in a second. As long as the number of uniform time samples is at least a constant times what you see on the right, So logarithmic in k, the number of active modes, inversely proportional to delta f, meaning if you have a pair of closely spaced frequencies, you have to take more samples m in time. And then inversely proportional to epsilon, where epsilon is going to show up in the accuracy bound down below, then we have this guarantee. And this is a guarantee on the inner product between the true kth mode shape and the estimated one. We're assuming they're both normalized to unit norm. So this is a number that if it's equal to 1, we've perfectly recovered the mode shape. If it's smaller, then we're making an error. And the deviation from 1 scales like this. This is basically epsilon squared here. If you want to reduce that number, then you're going to pay more in terms of how many samples you have to take. All this stuff on the right is measuring how distinct is this amplitude AK. So AK was the amplitude of the weight on the amplitude of the sinusoid on the kth mode, a function of the initial conditions of the structure. If that weight was very different from all the other weights, then this term will be small. Otherwise, this term could be relatively large. So there's this kind of peculiar fact that these amplitudes need to be kind of separated from each other in order to identify the respective modes. But that is fairly natural because of the way we're using the SVD to estimate the modes. Yeah.
Yeah, this is like, sorry, say something about the singular vectors, right singular vectors of the matrix.
Left singular vectors, yeah.
Well, how about the right ones?
No.
So could they approximate the frequencies?
So hold that thought for a minute. We'll talk about kind of the right side of the matrix in just a minute. To summarize this bound and compare with what we're going to see on later slides, as long as m grows logarithmically in k and like 1 over epsilon delta f, then just to kind of summarize that error bound, you could say like the error, roughly speaking, is like epsilon over the separation of the respective magnitudes. Okay, so as a potential way of reducing dimensionality, then we thought about what if you sample randomly in time instead of uniformly in time. So consider the same matrix we had on the previous slide, n by m. But suppose we just sample randomly in time and we just keep a small number of columns from the original matrix. So actually, if we do that, we don't even need to sample the ones we're leaving out. In hardware, you could have just skipped over those samples, or if you already took them, you could just throw them away. So you do this at each sensor. We call this synchronous random sampling because they're all taking samples randomly in time, but all at the same time instance when they sample. We'll look at asynchronous in a few minutes. And again, m prime is the total number of samples that they end up keeping. So for this, we showed that as long as m is basically the same as on the previous slide, this being m, sort of the number of samples from which you're selecting, then you only need m prime to be like k log k over epsilon squared. How to compare this number and this number? Well, keep in mind this one depends on delta f. And so when delta f is sufficiently small, when there's some pair of closely spaced frequencies, this bound can be much bigger than this bound. And actually, this is saying that the number of samples you actually need to keep is essentially scaling like k, which is really the number of degrees of freedom per sensor that you have. So the total amount of time, kind of the width of this matrix, is not different than the previous slide. If you have some pair of closely spaced frequencies, really you have like a pair of sinusoids whose frequencies are almost the same as each other. This shows up almost everywhere in signal processing. If you have two sinusoids and you want to distinguish them, you need to wait long enough for them to get out of phase, right? And the closer those frequencies are, the longer you have to wait in time. That's still true here. But the story of this bound is that you don't have to take a lot of samples during that time span. You don't have to keep sampling at the Nyquist rate. You can sample at a much lower random, with random intervals. So, Armin, to come back to your question, relating to the right matrix. So why does this work? Here's our signal model. X of t is this combination of modes with exponential weights. So therefore, if we think about our data matrix and just basically plug this equation into the data matrix, then it follows that x can be written in this form. This is not an SVD, but this is just a factorization that comes from the equation up here. What it has are the mode shapes on the left, diagonal matrix containing the amplitudes in the middle, and then a matrix containing these sampled complex exponentials on the right. These correspond to the various frequencies, f1 up to fk, and the various sample times, t1 up to tm. Okay, so this is not an SVD, but it looks a lot like one, especially because this matrix has columns that we have assumed are orthogonal. So we have a unitary matrix times diagonal matrix, almost times a matrix whose rows are orthogonal. If they were perfectly orthogonal, this would be a valid SVD. And it would explain why when you take an SVD of x, you actually recover the right mode shapes. So the kind of story in why this all works is that if you choose these sample times well, you make the rows of this matrix virtually orthogonal. They're all just sampled sinusoids, and sinusoids like to be orthogonal if you give them sort of enough time or if you sample them in the correct way. So either you sample for a long enough time or you choose these sample times randomly, you make these things virtually orthogonal. So this also kind of suggests that when things are working well, if you take the SVD of your data matrix, not only do you get an estimate of the mode shapes, but you get roughly sinusoids over here from your right singular vectors. And if you actually do this and take the FFT of your right singular vector rows, that gives you a pretty good estimate of your modal frequencies. So you can estimate modal frequencies from the POD, but it's not something we really dived into here. We also looked at another compression strategy. In this strategy, we have our data matrix. This is the same matrix we've been talking about. We consider, though, compressing it by multiplying it by a random matrix. So this matrix right here, let's think of as being random Gaussian matrix, or it could be just a random matrix of ones and minus ones. What that ends up doing, if you look at your dimensions here, every row of this matrix ends up getting compressed down to a shorter row. We go from m uniform samples down to m prime compressed samples. And that happens for each row in this matrix. Now, this can actually be done before you centralize your data. If you have one row of data at sensor number 1, you can compress that at sensor number 1, get this row, and then transmit that row to your central node, the central processor. The error bound, or the bound here, is very much like the bound was for random time sampling. You still need to possibly sample for a long time if you have closely spaced frequencies, but in that amount of time, the number of compressed samples you need to keep basically just scales like the number of degrees of freedom in the problem. So we will return to these different sampling strategies in a minute. I want to show a quick experiment here that this really works on compressed data. And again, we did not invent this algorithm. This is kind of a classical, off-the-shelf, quick and dirty modal analysis technique, but it's very cool to see it work on compressed data. So going back to this bridge data, there were 18 sensor nodes, and we had access to 3,000 uniform time samples from each one of those nodes. There's 3 dominant mode shapes, which we saw earlier. We'll see them again. We compressed this raw data from 3,000 time samples down to just 50 Gaussian measurements. So we multiplied by a Gaussian matrix of size 50 by 3,000 to reduce the dimensionality. So we basically have compressed the data by a factor of 60 and then try to estimate the modes. Okay, here's 3 plots because there's 3 active modes. And the blue shows our best attempt at extracting the ground truth mode shapes. this is a real structure. We don't know what the ground truth modes are, right? There's slight nonlinearities, there's external wind, there's noise. So we don't know what the true ground truth is, but we can estimate it from having enough real data, and we use a popular technique called FDD for doing that. And then the black curve shows the estimated mode shape. This is a function of the spatial position going from 1 to 18. The estimated mode shape, if you try to reconstruct from the 50 compressed samples at each sensor, if you try to reconstruct to the length 3000 signal by using sparsity as a prior, sparsity in the frequency domain. You do that and then you run FDD. That works pretty well on sensor number 1, but it kind of falls apart on 2 and 3. In black, we show the correlation between the true mode shape and the estimated one. 0.94 apparently in structural engineering is pretty good, somewhat useful. These other numbers are more questionable. But if we just run the POD on the compressed data, so we're just taking an SVD of one SVD of a matrix of the compressed data, which has size 18 by 50, then we get the mode shape shown in red. And those are a good approximation. All three of them are good approximations to the true, or our best idea of what the true mode shapes are from the structure. So significant compression of the data, followed by a very simple algorithm, gives a surprisingly good estimate of these mode shapes. Okay, so that was a very classical technique, and I'll revisit some of the shortcomings of that in a minute, but we're also interested in analyzing a more modern technique known as atomic norm minimization. So this also involves kind of a decomposition of the data matrix X. It is based on the observation that you can write X as a particular structured sum of rank 1 matrices. So phi k are the mode shapes, ak are the amplitudes, and fk are the frequencies. E here is going to denote a vector, a row vector. E star is a row vector, so E is a column, containing samples of a sinusoid. E of f contains samples of a sinusoid with frequency f, sampled at times t1, t2, up to tm. Okay, so the data matrix can be written as a very special structured sum of rank 1 matrices, all consisting of some unknown mode shape, times, right, this is an outer product, column times row, a vector which is a sampled sinusoid. So that suggests using tools from sparse regularization that involve a dictionary built out of rank 1 matrices, each one consisting of some vector, outer product with a sinusoid. To kind of keep things under control, we have to make sure that vector, we'll call it bk here, has unit length, unit norm. The atomic norm minimization framework gives us a framework for doing this optimization. So given X, or even given partial information about X, we can solve a sparsity regularized inverse problem to try to find the set of mode shapes and mode frequencies which best describe X in the most concise manner. I'm kind of skipping over some of the details about how you solve this atomic norm minimization. It turns out to be the solution to a semi-definite program. So you can use SDP optimization to do this, as Gongguo would have talked about in more depth in his talk. Whereas Gongguo focused on the single signal case, this is kind of a multi-signal or matrix-based optimization that we're looking here. And some previous researchers, Yang and Shi and Li and Qi, studied this same problem that we're talking about here, showing that you can minimize the atomic norm. And assuming you have no noise in your data, there will be situations where you can get exact recovery of the mode shapes and the mode frequencies. So unlike the POD guarantees, which were at best only ever approximate, there is a setting in which you can perfectly recover the mode shapes and the mode frequencies. So I will summarize some of their results as well as present some of our new results. And what we're going to do is step through a few different sampling and compression strategies. So we already saw uniform time sampling. Remember with POD, we needed M to scale inversely with delta F. We only got an approximate recovery guarantee for the mode shapes, which is true. POD only, really does give you an approximate recovery. And that required the mode shapes to be orthonormal. But with atomic norm, Yang and Shi showed, again, you need a very similar guarantee on M, actually. You really can't get around this. You need to sample long enough to let these sinusoids start to distinguish themselves. However, once you do that, you can perfectly recover the mode shapes and frequencies with its atomic norm minimization. Also, they make no restriction on the mode shapes themselves. They do not need to be mutually orthogonal, which is a big generalization or big relaxation of a constraint here. We also already looked at synchronous random sampling, and our bound there showed that although you couldn't reduce M for POD, you might be able to take fewer samples during that time span. With atomic norm, Yang and Shi showed again that you can't reduce M, but during that time with the atomic norm, you can get by with fewer time samples, essentially scaling with K. So random sampling can allow you to reduce the number of time samples that you have to keep, this as circled in red here. Again, it's an exact recovery guarantee. One limitation of this result was that it does assume that the mode shapes are generated randomly. So they use kind of a probabilistic analysis, and aside from the randomness of the sampling times, they needed to assume that the mode shapes were randomly generated. We can now think about different strategies that weren't really appropriate in the POD setting. For example, asynchronous random sampling, where now the sensors are all sampling randomly in time, but not at the same time instance. Let's say they keep M prime samples from each row of this matrix on average. You can still solve the atomic norm minimization problem. Actually, the bound on M prime that you get, this is from Li and Chi, is very similar to the case of the synchronous random sampling. So both strategies allow you to take random time samples and reduce the dimension of your overall data set. This also requires the mode shapes to be generated randomly. We've also previously talked about the random temporal compression, where you multiply each row of your data matrix by a random matrix to reduce its dimensionality. Now, for the atomic norm, we're going to consider the case where we use a different random matrix for each row that we're compressing. So this would be like every sensor does a different random matrix multiplication. In this case, we've showed that on average the number of compressed samples you need, again, scales essentially like K, the number of active modes. So even though delta F might be small and you have to sample for a long time, the number of compressed samples you need to keep during that time interval could be much, much smaller, and essentially scales like the number of things you're really trying to estimate about the structure. So you really can't do much better than this K right here. If you look at the probability in some of these bounds, won't go into too much detail here, but the other probabilistic bounds about random sampling by Yang and Shi and Li and Chi, they actually had probabilities that get worse as the number of sensors increases. So what that suggests is that if you were to have more sensors, you would need to take more random samples, M prime, according to their theory, per sensor. So more sensors and also more random samples per sensor. I think this is contrary to intuition and also contrary to experiments, because as you have more and more sensors online, they're all observing something in common, right? They're all observing sinusoids that have the same set of active frequencies. And so in fact, the problem should get easier as you have more and more sensors and not get harder. Our probability bound here scales in the correct direction with the number of sensors n, meaning that as you increase the number of sensors n, you can actually slightly decrease the number of samples per sensor. which again is in the right direction as far as the simulations go. Our work here also allows for arbitrary mode shapes. It does not require the mode shapes to be randomly generated. Yes?
Can we subsample the rows as in sensors? Can we draw some of the sensors and extrapolate them?
Yeah, so I think really any of these theories. Yes, so the question was, can you subsample the rows of this matrix, keeping only certain sensors and throwing away other sensors? So you definitely can as far as estimating the frequencies. Really all these theories would allow you to do that without much difficulty. However, the actual mode shapes are defined across all n sensors, and so you could estimate the mode shapes on the sensors you keep, but the information would be completely lost for the sensors you throw away.
But in a sense,
Use the microphone, yeah.
well, the sensors that are nearby, they are probably they have very similar information.
That's
so
true.
That adjacency might help. I mean, I see your point. If you lose the whole row of the matrix, it's you can't get it back. But this extra assumption,
Right, if you had some kind of smoothness assumption or coherence assumption about the kind of spatial regularity of these things, then certainly you should be able to incorporate that in. That makes a lot of sense, but it's not something that we've thought about very precisely. Yeah. Finally, we looked at one last technique for doing the compression. This is random spatial compression, where kind of similar to what Armin just asked about, we can actually compress the data matrix in the vertical direction, in the spatial direction. So here we think about, what if we take each column of the matrix and we compress it down to one single number? And the way we do that is by taking a random linear combination of those elements. It would be like if everybody in this room was a sensor, right? And I snap my fingers, we all take a displacement reading from our position on the bridge, and then you all multiply that by a random number, which is also known to me, needs to be known. And then everybody shouts their number at the same time, and then I add them up as I hear them, right? And so that would be very difficult, as I just described, but you can do this in analog hardware. You can have these things do kind of a phase coherent transmission of their numbers wirelessly, which then gets added up at that central node. This is a scheme proposed in compressive wireless sensing paper from 2006. I also think that there's interesting potential applications of that compression strategy in fiber Bragg grading sensors, FBG sensors, which are kind of wired fiber optic ways of doing motion monitoring on structures. And as I understand, there's people here at Alan Turing who are interested in those sensors as well. For the atomic norm minimization framework, the story is very similar, that ultimately we need a number of measurements m that scales like the number of degrees of freedom that we're trying to estimate. It also needs to scale like 1 over delta f. But it could be that once you've satisfied this, driven by your closest pair of frequencies, it could be that you have also satisfied this. Meaning you could have already compressed, if your data matrix works with uniform sampling, you could compress the entire data matrix in this scheme, get a 1 by m vector of compressed data, and still be able to extract the mode shapes and the frequencies. This does assume the mode shapes are randomly generated, so it's not quite as general as our result for the random temporal compression. So in my last few minutes, I'm just going to kind of summarize a few takeaways. We've talked about a lot of different results here, so what are the main themes? When delta f is small, that being the spacing between the closest pair of frequencies, or when you think delta f might be small, right, if you want to have sampling strategies that will work in case your frequencies turn out to be close to each other. All these methods require sampling over a long time span. You really can't get away from that. But during that time span, you can collect a relatively small number of samples or compress your data to a relatively low dimension. And all the compressive strategies we looked at have bounds that, aside from log factors, scale with the number of degrees of freedom, the number of things that you're actually trying to estimate in the structure. These were some simulations, synthetic simulations with 5 sensors, 3 active modes, and with kind of randomly generated mode shapes, but not orthogonal. We made sure that one pair was correlated with each other. For all the random sampling and compression techniques, we took a total of 100 compressed samples, either 20 samples per sensor over 5 seconds, or 100 total compressed measurements from the spatial compression technique. And these probabilities show the chance of doing, or the probability empirically of recovering successfully the mode shapes and the mode frequencies exactly. The uniform techniques refer to uniform sampling with an equivalent number of total uniform samples, either taken, right, instead of sampling, let's say, slowly and randomly over 5 seconds, we could sample quickly and uniformly over 1 second. That's this technique. That doesn't work. Or we could sample slowly and uniformly over 5 seconds. We just sort of round our samples to a uniform grid. But this is 5 times below the Nyquist rate, so we're sampling pretty slowly here. This actually does work for recovering the mode shapes, interestingly, but it does not work for recovering the frequencies, in short, because of aliasing. So we have undersampled the Nyquist rate by a large factor, and we're sampling uniformly, so there's just inevitable aliasing that you can't undo when this happens. So this was just showing that for all these techniques, the real scaling complexity, the measurement complexity was scaling linearly with the number of active modes, or the number of degrees of freedom that you're trying to estimate. So POD, while widely used, only returns approximate solutions, and it's most accurate when the mode shapes are orthogonal. This is 2 experiments, one with orthogonal mode shapes and then one with non-orthogonal mode shapes. And with the orthogonal ones, the true mode shapes are shown in red. The recovery from POD is shown in blue. This was with 80 uniform samples, but then compressed down to just 10 samples per sensor. So all the POD estimation is being done with just 10 measurements per sensor from each of 10 sensors. And actually the blue mode shapes are pretty good approximations here to the truth when the true ones are orthogonal, but when the true ones are not orthogonal, then the POD is limited in how accurate it can be. But in both cases, the solution from the atomic norm minimization is shown in black, and in both cases it perfectly agrees with the true mode shapes here. Synchronous versus asynchronous. So if you're doing random time sampling, should all your sensors be sampling at the same times, or should they be sampling at different times? Well, you can imagine this thought experiment. If all your mode shapes are correlated, and if every sensor is sampling at the same times, they're really not collecting very diverse information. They're all almost seeing the same signal, and they're all sampling it at the same time, so they're not really contributing much new. But with asynchronous random sampling, even in the extreme case, if every sensor was seeing the exact same signal, but if they're all sampling it at different times, then they're collectively getting a lot more information about those signals. So all that to say that asynchronous random sampling should in general be better than synchronous, and that's true in simulations. Here was one where the probability of recovery was higher with asynchronous sampling than with synchronous, but it's not yet reflected in the theoretical analysis. And finally, again, as you have more and more sensors, these problems should become easier and not more difficult. We confirm that with our theory for the random temporal compression. And this is just one experiment that kind of illustrates that. So here we took 80 uniform samples, we compressed them down to different numbers of measurements m prime, and that's the x-axis here. This is a plot of the probability of doing successful recovery, and the solid curves show the atomic norm minimization that we've been talking about. The different solid curves, denoted by these different numbers, show the different number of sensors that we're dealing with. So 2 sensors up to 16 sensors. And this confirms, as you add more and more sensors, these probabilities are going up. The problem is actually getting easier with a fixed number of samples per sensor. So again, m prime is the number of samples or measurements per sensor. You fix that, but you add more sensors. The problem is getting easier. In contrast, these dashed lines show what you would get if you tried to solve this joint sparse frequency estimation problem separately at each one of your sensors. So you just do atomic norm minimization separately across all your sensors and then see if everybody agrees on what the frequencies were. That gets harder and harder, right? As you start having more and more sensors, you have an increased probability of failure. You're basically doing a union bound over n independent events. So you're adding up those failure probabilities. The problem gets harder. So doing separate recovery gets harder, but joint recovery gets easier with more sensors. So I'll stop there. We have many open questions we're still interested in, including characterizing the differences between synchronous and asynchronous random sampling, characterizing the dependence on the number of sensors and some of the theories where we think there's still room for improvement. More generally, from the structural dynamics perspective, it would be valuable to incorporate things like damping into our analysis. We have some thoughts on how to do that. And then also things like forced inputs, either considering random inputs to the structure or inputs that we design ourselves to help with the identification. Those are sort of practically relevant in the real structural health monitoring field, but not something currently within the scope of our analysis. So thanks for your attention. If there's time, I'll be happy to take any questions.